Okay, so we're going to have a little bit of an interlude here, and we're going to talk about something called Farkas's lemma and convex cones. And now these are going to be really important. So Farkas's lemma is going to be important for us to prove the Karush-Kuhn-Tucker conditions, the KKT conditions, which are a really important aspect of constrained convex optimization. And convex cones are going to be a useful idea for us to know as we go on in this subject. So it's a little bit of an interlude, but we'll use this stuff later. So okay, so what is Farkas's lemma? So it's this, and it looks a bit complicated. It's barely worth me reading this out because it doesn't make a lot of sense at the moment. But I'll tell you it anyway. So if A is a real valued m by n matrix, so a rectangular matrix, doesn't have to be square, then the system AX equals B, where X is positive, is a solution X if and only if for every m-dimensional vector U, if A transpose U is greater than 0, then B transpose U is greater than or equal to 0. And so you look at that and you think, what does that really mean? And so the point of this video is actually not to prove this lemma. So the proof of the lemma is in the notes, and you can check that out. But it's to give you some meaning, some geometrical sort of understandings or some intuition for what on earth does this lemma actually mean. So it turns out it's actually, there is actually a geometrical sort of intuition for this, which is useful for us to go through. So the algebra there, I don't expect that to mean, for that to mean a lot to you at this point. But really what this lemma boils down to is something like this picture here. So the idea of the lemma is if we have a matrix and we take the columns from that matrix, then the columns of those matrices will form a set of vectors. So here's a two-dimensional example where I've got a 2 by 2 matrix, which has got two vectors A1 and A2. So those vectors are going to be what, 0, 1, and 1, 1 in this case. And those vectors describe some region. If you take all of the positive linear combinations of those vectors, so the space that's sort of between those two vectors is called a convex cone. And then basically what Farkas's lemma says is that if I take any vector B, so you see some vector B here, then the vector B either will lie in this blue region, right? It will either be lie over the top of that blue region there, or it will lie outside of the region, in which case I can put a line between, a dashed line between my vector and my blue region here, right? So this dashed line is something that separates the vector B, the red vector B, from my blue region, and that vector U is just normal to this dashed line here. And that's all that Farkas's lemma is saying, actually. When you boil it down, it's basically saying, once you have this region, which is described in some sense by your matrix A, you take any vector, the vector either sits in the blue region or it's separated by this line, by that brown line. So geometrically, what the lemma says is that either a vector B is in this blue region, which is called a convex cone, and I'll define that in a sec, or there is a separating hyperplane. So this dashed line here, the brown dashed line, is a hyperplane in 2D, and it's a line in 2D, and that hyperplane sits between the vector B and the blue region, the convex cone. So one of those things happens, but you can't have both happen. You can't be outside the convex cone and inside the convex cone. So you can't be separated from the convex cone and inside the convex cone. That's it. There's two things that can happen. Vectors either sit in the blue region or they sit out, in which case they're separated by a line. That's the whole lemma. So we need to go a little bit deeper. I've introduced a term here called a convex cone. So we'd better define that. So a convex cone is for any rectangular matrix. If I call the columns of that matrix a series of vectors, A1, A2 through to AN, then if AX equals B, that means that B is a linear combination of the columns of A, right? So that is, this here, this expression for B is a fancy way of writing AX equals B, right? For some values, X1, X2, up to Xn, if I can find those X1 through Xn, then I can write B in terms of a linear combination of the columns of my the columns of my matrix A. That's what it means to solve AX equals B. It's just another way of writing it. So if we say that all of those x's are positive, right? So if my solution to AX equals B has got all of my x's be positive, so if my vector x is positive, then the set of all points that you generate is called the convex cone, right? So that's what it means to be a convex cone. So essentially, it's a set of all of the linear combinations of the columns of A, right, where you have positive coefficients. That's all it means. We can do some pictures of these things. So here's the 2D example that I just showed you of a convex cone. And here I've written out the matrix. So if I take the matrix 1, 1, 0, 1, right, the first column of that matrix A is vector 1, 0. So it points along the x-axis, right? The second vector here, second column vector is the vector 1, 1. So it points diagonally up to the right. That's my vector A2. And then all of the points for which the linear combinations where I have positive values are going to be the region that's in the blue here, right? So the convex cone for this matrix A, for these vectors 1, 0 and 1, 1, is that region that sits in between the two, right? So that's the idea. So you take a matrix, you write down the column vectors, and then you basically get the region that sits between all of those, and that's called a convex cone. In 3D, so this is full credit to Tony Roberts here, who produced this amazing, this is a stereoscopic picture. So if you cross your eyes, as I'll try to do on my screen now, if you do this like a magic eye, and you actually cross your eyes on those images, you can actually make this picture be 3D. So try that, and you can see a three-dimensional region here that's defined by 3 different vectors. So here I'd have a 3 by 3 matrix with 3 different vectors, A1, A2, and A3. You can almost tell what they are. They're written in the book. And then the convex cone is the region now, a 3-dimensional region that sort of sits between. It's defined by those 3 vectors. So that's the convex cone. And so now we can come back to having some intuition for what that is. We can come back to this Farkas' lemma. And remember, so Farkas' lemma now says, now we know what a convex cone is, it says that a vector B is either in the convex cone, so that's the picture on the left here, right? So I either write down a vector B, and it sits in this blue region, or I can write down, or B sits outside the convex cone, in which case I can put a hyperplane that separates between the two. So I can be, for any vector B, I can be in either the left-hand picture or the right-hand picture, but not both. And that's it. So hopefully now, so maybe if I put back what this means algebraically, so now I can map between those 2 pictures. So Farkas' lemma says that either one or other of the following holds. So any vector B is in the convex cone of the columns of A, right? So B is in the convex cone, or there exists this separating hyperplane, and what that means algebraically is that there exists some vector u such that A transpose u is positive for every A, right? And that B transpose u is less than 0. That's an algebraic way of writing that this u exists such that B is on the left-hand side, B is underneath this hyperplane, and the convex cone is above this hyperplane. So it's an algebraic way of writing down this idea. There is a separating hyperplane between vector B and the cone. And having that intuition, we can come back to the lemma itself. So, you can maybe now start to see that there is a mapping between the solutions of AX equals B. So there are positive solutions of AX equals B if and only if for every vector u, either A transpose u is greater than, for every u, if A transpose u is positive, then B transpose u is positive as well. These things link back to this algebraic description and this geometric description. So, you know, it's a strange, it's an unusual sort of lemma. As I said, we will use it to prove a theorem, to prove the Kurushkin-Tucker condition soon. But hopefully, you know, I want you to, whenever you use this, I want you to keep in that in your mind that idea of the convex cone and vectors either sit inside the convex cone or with a separating hyperplane between the vector and the cone. And that's it.